Welcome to Control 4 Driver Development Essentials. My name is Peter Cosenza. In this video, we'll look at how you can use Control 4's AVSwitch driver development template to shorten the development process behind creating an AVSwitch driver. In watching this video, you will gain an understanding of the areas of the driver template that require your development attention, as well as libraries and common files that can be simply leveraged to assist with the heavy lifting involved in creating an AVSwitch driver. Throughout this video, we'll rely heavily on a data flow diagram, which provides us with a physical representation of the driver template. This diagram and accompanying documentation is also provided as a download here in the Control 4 University, where this video is accessed. Before we begin, it is expected that you are already familiar with the architectural and development concepts outlined in the driver development training modules. This includes the 201, 301, 401, and T101 video series. Additionally, we recommend watching the C4Z and driver template introduction video if this is your first time using a Control 4 driver template. You may find it useful to review the information offered in those training modules before proceeding to develop template-based device drivers. In this video, we'll examine 3 data flows that cover the most significant communication scenarios you'll encounter when deploying AVSwitch drivers. These include communication between a device and the Control 4 user interfaces, sending commands from Control 4 user interfaces to a device, handling commands that are unique to the device and not supported through the Control 4 device proxy. Now, let's take a look at the template workflow diagram we mentioned earlier to understand how the various areas of the diagram represent an AVSwitch driver and how data moves through it. Starting at the left, we can see the device, or an AVSwitch in our case. This represents the physical device we're writing a driver to support. Immediately to the right of the device in the diagram, we can see 3 Lua files: device messages.lua, proxy commands.lua, and device specific commands.lua. Here are those same files within the AVSwitch driver template. These files represent the areas within a driver template where you, as a driver developer, will be working. You'll also notice a line dividing the diagram into 2 sections. All of the areas to the right are provided through the driver template and are used to facilitate data flow. You, as a driver developer, do not need to modify any of these areas in your development work. We can also see in this area a representation of the device proxy and the Control 4 user interface. Now that we have a feel for the layout of the diagram, let's look at a data flow example and see how the AVSwitch driver template handles communication coming from our AVSwitch to the Control 4 user interface. We'll start at the left with item number 1. Here we see the AVSwitch sending a message via its communication port to update the Navigator UI or Composer's device control UI. We can see at point number 2 that incoming data from the switch must first be parsed by you, the driver developer. This work happens in the device messages.lua file found in the driver template. Let's take a closer look at this file in the driver editor environment. All messages sent from an AVSwitch need to be parsed into a format that the Control 4 AVSwitch proxy can understand and ultimately be handled correctly by your driver. These messages contain data that directly impacts what is displayed on the user interfaces through the use of the AVSwitch proxy notifications. All of the proxy notifications are predefined for you in the AVSwitch template. They can be found in the AVSwitch proxy class.lua file. When we open this file and scroll to the bottom, we'll find all of the AVSwitch proxy notifications. They are under the AVSwitch proxy notifies header. Remember, there is no need for you to edit any of these notifications. They are called after you parse the message from the device and then create a new function that passes the parsed data into the AVSwitch proxy class.lua file. The new function that you create will call one of these predefined notifications. The notification is then sent to the proxy using the send-to-proxy API. This results in the system user interfaces being updated with the message data from our AVSwitch. All parsing of data messages from our AVSwitch occurs inside the device.message.lua file. If we open the file, we can see that sample functions have already been included for you. Note the use of to-do in the functions. These serve as informative descriptors to help you find the areas in code that need your attention, as well as understand what type of data the function handles and possibly any parsing considerations. Perhaps the most difficult job for you as a driver developer will be to parse the incoming messages from the AVSwitch into a format that can be sent to the Control4 proxy and displayed as usable data on the user interface. If the AVSwitch sends multiple messages within one packet, each message must be parsed so that it can, in turn, call a unique notification function that correlates with the message type. All parsing of device messages is done using the handle message function, which is also in the device.message.lua file. Here it is at the top of the file. Let's consider, for example, that our AVSwitch sends a message whenever the volume level is changed. We want to use the data in that message to update our UIs with the AVSwitch's latest volume information. The incoming message from the AVSwitch might look something like this. The protocol for the AVSwitch with which we are working uses a three-letter prefix in its messaging that indicates the functionality of the message. In our example, VOL means volume. Next, the protocol sends a number which represents the zone whose status is being reported. So here, the number 1 indicates that the message is applicable to Zone 1. Next, a colon delimiter is sent, separating the zone data from the volume data. Finally, the protocol sends a value at the end of the message. In our case, the current volume level is 50. And we know from reading this particular AVSwitch's protocol documentation that the message values sent regarding volume levels are in percentages. Without modification, this means nothing to the AVSwitch proxy. We first need to parse this incoming message into a name-value pair, with the name being the command from the device and the value being its parameter. Once the data is currently parsed into name-value pairs, we need to create a new vol function for this message. The value is passed as a parameter to our new function, and at this point it can be handled by the AVSwitch proxy. The AVSwitch proxy class is defined in the AVSwitch proxy class.lua file. This file provides a template API, or a group of functions that can be called by our newly created vol function. All of these APIs are recognizable by the AVSwitch proxy and can pass the data on to our UIs. The names of these API functions begin with dev underscore. For example, here is the function for handling the AVSwitch's volume. It's called dev underscore volume level changed, and it has 3 parameters. Output, which correlates to the connection output bound to the zone whose volume is changing. C4 level, which is the current volume expressed in Control4's volume range, which is percentage. Device level, which is the current volume expressed in the device's volume range. This could be percentage, but in most cases will be an audio scale. Knowing this, we need to go back into device_message.lua file and build a new function that is based on the vol messages coming from the device. In this example, we'll make the assumption that the message coming from the device adheres to the same volume percentage scale that is supported through the Control4 AVSwitch proxy. The new function we need to create looks like this. Based on this example, we can see that our protocol uses a column delimiter within the string of the message. Let's look at the function line by line to understand how it handles volume level, so the Control4 proxy can pass this information up to the system user interfaces. Note that line 1 contains a reference to the Lua table dev message. This table holds all the functions handling messages coming from the device. Following the dot, we see the name of the device function, or VOL. This is the name portion of our name value pair. This is followed by the value portion of our name value pair. It is data in this variable that will eventually be passed as a parameter up to the UI. Let's look at this function line by line to understand how it handles volume level so that the Control4 proxy can pass this information up to the system user interfaces. In this line, you would handle any conversion that may be needed to parse the incoming parameter into the correct volume and zone formats for the AVSwitch template. Here, we see an example of the Lua string match function, which is part of the Lua string library. If you are not familiar with string match and the other functions in the Lua string library, you can find full documentations at lua.org. What you will find particularly useful is the use of captures and patterns in Lua string functions. Understanding these conventions will greatly simplify your driver's parsing code. In our function here, string match is used to capture the number before the colon and return it to a variable named device output, and then capture the number after the colon and return it to a variable named device level. So at this point, we now have the output ID and the volume level based upon the ranges defined in the device's protocol. The next two lines of code is where we would convert these values into the value ranges required for use in our proxy. In this example, we are assuming that no conversion is necessary, so we will merely pass the values directly from the device variables into new variables named output and C4 level. While this may seem redundant from the perspective of this example, being explicit will make your code more readable and also more portable. Finally, we see a call into the AVSwitch proxy class.lua file and its appropriate API named dev volume level changed. As you see, this function takes three parameters: the output ID and volume level in the Control4 range, as well as the volume level in the devices range. This example contains all the logic needed to create a notification. When the call is made, the template API dev volume level changed will take the parsed and possibly converted variable from the AVSwitch and pass it on to the AVSwitch proxy, which will notify the UIs of the current volume level, which in our case is 50. It also stores the volume in the devices range for use in future volume ramping sequences. Now, let's look at another example where the AVSwitch does not adhere to Control4's AVSwitch proxy's use of a volume percentage scale. In this example, the message coming from the device also uses a colon delimiter, but the message values from the output ID and the volume level need to be modified so that the proxy can understand them. Consider that this AVSwitch sends a volume message that looks like this. The new function to handle this message would look like this. Once again, let's look at the function line by line to understand how it handles volume level so the Control4 proxy can pass this information up to the system user interfaces. You will notice that the line at the beginning where we parse the device message using string match and the last line where we call into the AVSwitch proxy class have not changed. This makes sense since we are assuming the same device message syntax, and of course the AVSwitch proxy call requires the same parameter values. What is different in this example is the processing that we need to do with the device variables in order to convert their values to the applicable Control4 values. First, let's look at the output ID. Keep in mind that in Control4 templates, the output ID is the mod 1000 value of the actual output connection that you have defined in the XML connections section of your driver. For this example, the driver's output connection IDs start at 0, and the device protocol starts the output IDs at 1. So for any given output, we will need to subtract 1 from the device output ID when we wish to reference it in the Control4 driver. We need to convert the volume level. In our example, the device is using a volume scale that starts at -80 and goes to +20, whereas the Control4 volume range is 0 to 100. To do this conversion, we will use a helper function that is delivered as part of the AVSwitch template named Convert Volume to C4. This function takes 3 parameters: the current volume reported by the device, the minimum value in the device's volume range, and the maximum value in the device's volume range. The function processes this data and returns the converted volume value in the Control4 scale. To make this function more readable, the template includes 2 variables where you can enter the device's min and max values. We already have the device level, which was parsed in our string match line. Now, we see that the convert volume to C4 takes these values and returns the converted volume level and stores it in the C4 level variable. And finally, these values are used by the AVSwitch proxy function dev volume level change to update our proxy with the current volume level. Once we have handled all of the messages that the AVSwitch sends, which require being sent up to the UI in this manner, the Lua development work for handling device messages in our driver is complete. Now, let's change directions and take a look at communication flow coming from the UI to our AVSwitch. At step 1, the initiation of a command is sent to the device from user interaction through Navigator or Composer Pro control. At step 2, the proxy then calls into the Control4 API received from proxy, which, in turn, calls into the AVSwitch proxy commands.lua file using the prx_cmd command table structure. AVSwitch proxy commands.lua is a template file that receives the command from the proxy and handles it for you, the driver developer, by modifying its format as well as its parameters. For example, note that the use of device in the diagram will be reflected by the name of the device for which the template has been designed. For example, for an AVSwitch, the file name would be AVSwitch proxy commands.lua. At step 4, the AVSwitch proxy commands.lua file then calls into the AVSwitch proxy class.lua file. This is a template file that stores device-specific data within the driver template. It receives the modified commands and extracts its tparams table into one or many individual parameter elements for the driver developer. In doing so, it also modifies the format of the command further. For example, prx underscore command name tparams calls command name tparams dot parameter 1. At point number 5, this version of the command is then delivered to the proxy commands.lua file. Here is where you, the driver developer, needs to receive the command and its parameters, modify them in a manner that is valid for the device, and subsequently send the command to the device via the designated communication method. Now let's take a look at an example of the functions that are included in the proxy commands.lua file. In doing so, you will also see how the AVSwitch template uses Lua tables to store most of the data required to build functional commands. By using tables in this manner, we're able to keep the actual function code in small, easy-to-read code blocks. Here we see the setInput function as it is delivered in the template. You will notice that it supports IR control, which will not be addressed in this video since it uses a very different command structure than serial and IP drivers. So, for serial and IP drivers, there is only one line that you, the driver developer, will need to modify. As we drill into that line, we see that there are three main components. First is the command variable, which will store the command string that will ultimately be sent to the device. The remaining two elements are what is used to build the command. Since most AVSwitch protocols will use the same syntax for input selection, all we need to do is store output string elements in one table and the input string elements in another table. These tables will be indexed by the output connection and input connection IDs. So when the command is sent by the proxy, it will take these IDs to the respective tables and get the correct input and output component and assemble them using the correct syntax for this device. For this example, let's assume that the protocol for input selection uses this syntax: OX:, IY, where X is the device's ID for the output and Y is the device's ID for the input. Let's also assume that the device IDs start at 1 and our driver's connections IDs start at 0. Here is our modified function. And here are the tables to support this function. The output command map table maps the value of the output connection ID, which has been modded by 1000, to the output command elements used by the AVSwitch's protocol for input to output routing. The input command map table maps the input connection name used by Control4 to the input command used by the AVSwitch's protocol. The input con map by ID table maps the value of the output connection ID, which has been modded by 1000, to a name value which includes the Control4 input value and the proxy binding ID for the device, which is stored in the constant AVSwitch proxy binding ID in this case. If you were paying attention earlier when we examined our modified function, you may have noticed a small twist to the input part of the command string. Here, we actually reference two tables. This enables us to translate the proxy command, which uses the connection ID, to the device command table, which uses the input name. Finally, we need to review the pack-and-queue command function, which will take this command, pack on any prefix or suffix if required, and then send the command to the device. Okay, let's take a closer look at pack-and-queue command. First, you will notice that this function has 3 dots for parameters. This is the Lua notation for optional parameters. This function is expecting up to 4 parameters, but you really only need to send the first 2. The first parameter is the name of the command that is calling this function. The second parameter is the actual command string that needs to be packed and sent. The third and fourth parameters deal with the amount of time that the command queue will wait after sending this command and before sending the next command in the queue. This time interval is referenced as the command delay in Control4 templates. All templates have a driver property that sets the default for this time delay in milliseconds. So, if you want to use the default value for any given command, you do not need to send the third and fourth parameters to the pack and queue command function. If you do want to override the default values, you can use the third parameter to override the value of the delay and the fourth to override the default time units. For example, you may wish to use units of seconds or minutes for certain commands like power on. Keep in mind that you should not change any of these lines of code. They are ready to go as is. Next, we get to the packing part of this function. Most protocols employ a syntax that require a terminating character or set of characters at the end of each command string, like a carriage return or a carriage return in the line feed. Since this is required on every command, there is no need to add it to each command table and command function in your driver. Simply define it once here in the pack and queue command and be done with it. The same logic also applies to any start character or set of characters that may be required. Also, some protocols use the same command strings for serial and IP communication, but may require different start or ending characters. Pack and queue command is already set up to handle that for you. And finally, we see a call to the queue command function in the connection class. At this point, our command is pushed onto the command queue. The command queue will take care of sending the command and popping the command off of the queue automatically. The set input function that we just reviewed is a good example of the multi-zone type functionality that needs to be supported in an AVSwitch driver. And we also saw how Lua tables make it easy to store the command information in a building block type methodology, which makes the function code easy to read and manipulate. But what about commands that are not multi-zone in nature, such as menu navigation commands? The AVSwitch template greatly simplifies the handling of those types of commands. All you need to do is fill in the correct command string in the CMDS Lua table that is included in the template. In our final example, we'll see how the AVSwitch template can handle device-specific commands that fall outside of the proxy definition. There may be some instances where an AVSwitch has some commands that are unique to that specific device, and the defined Control4 proxy does not have a command to natively accommodate that functionality. This functionality will need to be provided to the end user through Composer Pro by means of programming or events. Consider that an AVSwitch has a command which locks the front panel of the switch so that users cannot change settings directly on the unit. The current Control4 AVSwitch proxy does not have a command to support this. However, the driver developer can create a command to support setting locking the front panel. Creating a device-specific command requires entries in two parts of your driver. First, it must be declared in the config commands area of the XML. The XML code is what Composer Pro will use to present this command to the user. Then, a Lua function must be written to handle this command. The Lua function should be included in the device-specific commands.lua file found in the template. These types of commands are not sent to the driver through the Receive from Proxy API, but rather the Execute Command API. As stated above, they are initiated through programming in Composer Pro, such as a button on a keypad or a custom button on a device running Navigator. They can also be tied to events, which can display a pop-up on the UI. To handle a device-specific command successfully, your job as a driver developer will be to define these commands within the device-specific commands.lua file in the template. For example, we can create a command called panel lock. it has a state of unlocked or locked. Once our driver is loaded into a project, the user will be able to schedule the execution of this command or trigger the firing of this command based off of an event. This concludes the AVSwitch driver template introduction video. We hope that this helps you better understand how to take advantage of Control4 driver templates to create AVSwitch driver files in the future.